Hey everybody, welcome back to another Calculus 1 video. This video is covering the concept of implicit differentiation. The idea is this: what we've been doing so far, we have y equals 3x squared plus 6x minus 11. When we've been taking the derivative and getting dy dx, we've been explicitly solved for y. Y has been all by itself over here, and we've had the derivative of 3x squared, which is 3 times 2x, plus the derivative of 6x, which is 6, minus the derivative of 11, which is 0, and then we get this dy dx is equal to 6x plus 6, and that's it, no big deal. This is the explicit idea, but the truth is that this y doesn't have to be over here by itself. Right? We could have, say, 11 equals 3x squared plus 6x minus y, for example. That's the same expression, just in a different order. And then because of the way derivatives work, you can take the derivative of every single piece, because the derivative rules for sums and differences say that you just take the derivative of each piece. And so when I go to look at this, in this manner, the derivative of 11 is 0, the derivative of 3x squared is 6x, the derivative of 6x is 6, and then the derivative of y is dy dx. And so we just take the derivative first, and then we add dy dx to both sides, and we get that guy. So this is the idea of implicit differentiation, and I'm sure some of you are sitting there thinking, well, big deal. Why would we do that? It works just fine over here. Well, you're right, it does work just fine over here, but not all expressions, relations, are functions of x. You can't just solve for y, right? So here's an example where you have 2x cubed equals 2y squared plus 5. If we try to solve that for y, we'll get a plus or minus. We don't get just y by itself as a function. This is not a function of x. However, it's still a curve in space, and it still has tangent lines, and it still has all that kind of stuff. And so to find the derivative dy dx, we're going to do implicit differentiation. We're going to take the derivative of every single piece. Remember that the operator d dx means take my derivative, please. That's what the operator d dx means. It means take my derivative. It's just like a prime sign. This dy dx means I've had the derivative. I've taken the derivative of y with respect to x. So how do you do the derivative with respect to x of 2x to the third? Well, bring down the 3, and that's 6x squared. No big deal. Simple. How do you take the derivative of 5? You get 0. But now how do you take the derivative of 2y squared with respect to x? Well, here's the thing, and you got to be really, really careful with this. Y squared is stuff squared, because y is still the dependent variable and x is still the independent variable. And so that means when you're taking the derivative with respect to x, y is changing in terms of x, and so therefore y has an x inside of it. It's like a chain rule. So how do you find the derivative of 2y squared? Well, you bring the 2 down just like normal, so 2 times 2 to the first, but then I need to take the derivative of the stuff inside. What's inside? The y. The y was inside the square. And so we get 6x squared equals 4y to the first power times dy dx plus 0. And so the dy dx comes out of the fact that we are differentiating y squared with respect to x. Y is a function of x. It's not really a function of x, but it acts like one. It has an x inside of it. Y is dependent. Y depends on x. And since y depends on x, y is treated as a function of x with regards to the chain rule. Again, it's technically not a function, but it is a relationship that depends on x. And so you've got to think of it as the chain rule. And so here I am done with calculus, but I'm not done with this problem. Some of you guys who have been in my class know that I have been really emphasizing don't worry about simplifying right now, and that's true. up until now. But this is not simplifying. This is answering the question. I asked for dy dx, and I don't have it yet. I don't have dy dx by itself. So I need to divide both sides by 4y. 4y divides 4y. I'm left with dy dx on the right-hand side all by itself. And here I get 6 divided by 4 is 3/2. 3x squared over 2y is the derivative. If your original function, your original expression was not solvable for y, then I wouldn't expect my dy dx to not have a y in it also. All right, and so it does. It has x's and y's in it, and that's fine. And this is the final answer. Can't leave it up here. Can't leave it like this because that's not solved for dy dx. Okay. So I know it's a little bit different, but I do want you to try one. Here's one that's a little bit similar. 2x minus 7y squared equals 11. Very similar. I want you to find dy dx. Pause the video, take a couple minutes, and find that derivative. Okay, so what do? Once again, we differentiate every single piece in this implicit equation. It's not solved for y, and we're not going to be able to solve this one for y cleanly, so we're not going to try. Derivative of 2x with respect to x is 2. When these guys match, you just do it regular derivatives. However, in this case, it's y squared and x, and so what do? Bring the net 2 down. You get 7 times 2, which is 14y to the first, times the derivative of the stuff inside, the derivative raised to the power. The derivative of the stuff raised to the power is y, so the derivative of y is dy dx. The derivative of 11 is 0. So now I'm drawing this line once again. It's like a dotted line. I'm drawing that line to represent the derivative is done. I've differentiated, but I've not solved for the derivative, and since the algebra had not been done up here, I have to do the algebra now. So I'm going to subtract 2 from both sides. Negative 14y dy dx equals negative 2. Divide both sides by negative 14y. Reduce, and you get dy dx. 2 negatives make a positive. 1 over 7y. Okay? So that's the process. We're going to show you a couple of other things that can happen. Here we have a much more complex scenario with y's on both sides. Can't solve for y, so we're not going to even try. But here, what is the deal? Well, this guy is a product because remember, y has x inside of it. So 3x squared y squared, this is the first and the second term. And actually it happens again. 4xy is also a product. 4x is the first and y is the second. So we're going to have to do the product rule twice here. Once on the left-hand side with 3x squared y squared. We're going to do the product rule there. And once on the right-hand side, 4x squared is just normal, right? And then I'm subtracting. Don't forget to group everything the right way. 4x times y, that's another product. Here it's 3x squared times y squared. So when I go to do this derivative, this is the product rule, first and second. The derivative of the first is 6x times y squared, plus the derivative of the second, the first is 3x squared, the derivative of y squared is 2y dy dx, or some textbooks, and sometimes we will write it as y prime instead of dy dx. Same thing, remember y prime is the same as dy dx. But I want you to get used to being able to use both notations. So I'll do this one with y prime. The right-hand side, derivative of 4x squared is 8x minus the group. I got to group it because this is a product now, the derivative of 4xy. So you get the derivative of the first, derivative of 4x is 4 times y, plus the 4x times the derivative of the second. Now, the second is just y. What's the derivative of just y? Dy dx, or y prime, right? Y prime. So let's start. So once again, if you can get to here, you're not finished, but you do understand the basics of implicit differentiation. You figured out how to do basic implicit differentiation. What you need practice on if you're struggling from here on is, once again, algebra skills. And the algebra here is collecting like terms. All the like terms that have y prime in them have to be on the same side. So let's see what I have. I have 6xy squared. 3 times 2 is 6. I do want to simplify here as much as I can while I'm doing this process. 6x squared y times y prime equals 8x. Take this negative and distribute it, minus 4y minus 4x y prime. So now what am I trying to do? I'm trying to solve for y prime. I have a y prime right here, and I have a y prime right here, which means I want to collect like terms. I want to get them all on the same side. 6x squared y prime is on this side. I'm going to add 4x y prime to the left-hand side. So these guys are taken care of. And now I'm going to take this 6xy squared to the other side, and I have 8x minus 4y minus 6x y squared. So the deal again is that we want to collect all the y prime terms on the left and everybody else on the right. Okay, we're just collecting like terms. And then what can you do when this term has a y prime and this term has a y prime? Factor it out. So you factor out y prime, you're left with 6x squared y plus 4x. Here you have 8x minus 4y minus 6xy squared. And then you divide both sides by this guy in order to solve for y prime. So I divide by 6x squared y plus 4x. That divides this away. And then I get the 6x squared y plus 4x. So y prime is equal to this big ugly mess. I know, sorry, but that's the way it goes. And so that's what you got. Okay? So you guys try the next one. Here we've got e to a power, e to the y. So think of that as a chain rule. Y squared obviously is a chain rule. Take a couple minutes and try this guy, and then solve for y prime. We'll come back and go over it together. Hit pause and give it a shot. Okay, so let's take the derivative of each piece. One way to kind of do that in general is just to kind of write like this, take the derivative of everything. That's fine too, you don't have to write it for each one. The derivative of 2x cubed is 6x squared. The derivative of e to the y. Well, the derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. What's the derivative of y? dy dx, or if you wanted to write it as y prime, that's acceptable too. That's the way we did the last problem, so I'll do y prime this time. The derivative of y squared is 2y to the first times y prime. So if you've got a y and you're taking the derivative with respect to x implicitly, you're going to get a y prime somewhere in there. One quick thing I need to mention, you will never, ever, ever, never get y prime anywhere other than multiplied or added to something. You're never dividing by y prime. You never have y prime inside of a power. You never have y prime inside of another function. It's always times y prime or plus y prime if y is all by itself. Okay? So implicit differentiation is done. I am done the differentiation, but now I need to do the algebra. It's a little simpler this time. I'm going to subtract e to the y minus y prime to the other side. So you get 2y, y prime, minus e to the y, y prime. Factor out the y prime. And then you are left with y prime times this. Divide both sides by that. And you get 6x squared over 2y minus e to the y. And that's equal to your y prime. Okay. Now this derivative means the same thing, guys. This still represents the slope of the tangent line for this particular curve, but because it is not a function, it may have more than one tangent line at a particular point. It can do all sorts of weird stuff. Okay, so you just have to be aware of it. I'll give you one more example here if you need it. This is y equals sine of xy. Sine of xy is inside this sine function. So if I want to find y prime, okay, I'm going to take the derivative of both sides, derivative of y, derivative of sine of xy. Okay, So we get y prime equals, what's the big picture here? Sine of stuff. The derivative of sine is cosine. Okay? And then I'm going to multiply by the derivative of the stuff inside. What is the stuff inside? xy is just what? xy is a product. So I got to use the product rule. So I get the derivative of the first, derivative of x is 1 times y plus x times the derivative of y, which is y prime. So I'm done taking the derivative now. I have a y prime over here, but I have a y prime in here. So I got to solve for y prime. I can't solve for y prime in terms of y prime, so I'm not done. I got to distribute the cosine and break out that y prime and then collect like terms. So I get y times cosine of xy plus xy prime times cosine of xy. Put that guy to the other side, you get y prime minus xy prime cosine of xy equals y cosine of xy. And I'm going to factor out the y prime. So I factor y prime out of y prime, I divide that away, I get left with 1. Factor y prime out of here, you get x times cosine of xy. Here I've got y cosine of xy, and then we're going to divide both sides to solve for y prime. So y prime is equal to y cosine of xy all over 1 minus x cosine of xy. Okay? So guys, these do take a lot of practice. They're a little bit different, but they're not hard. You just have to get comfortable with the notation, and remember that every single time you take the derivative of a y with respect to x, you're eventually going to get a y prime or a dy dx somewhere along the way. And it's never going to be inside another function. It's just going to be multiplied on the side. Okay? So give a lot of practice there. They take a lot of practice, and start with some of the basic problems and then go to some of the more difficult ones and see what you can do. All right? Thanks.